Hello everyone, in this video we're going to go over base and problems. So first, let's convert each of the following numbers that are given in a particular base to the decimal base by expanding powers on the base. So for example, here we have this number on decimal or on binary base, and we're going to transform this into decimal base. So we have first 1, this first one. And then notice that this has 5 digits, so we're going to start by 2 to the 4. And then we're going to go with plus 0 times 2 to the 3, plus 1 times 2 to the 2, plus 1 2 to the 1, and then plus 0 times 2 to the 0. That's the reason why we start from 4, because we are going to power 0. So now let's take a look at what this is. So 2 to the 4 is 16, and this is 0, and then 2 to the 2 is 4, and then we're going to have a 2 here, and then we have a 0 here. So we have 20, 22. So this is 22, and of course this is in decimal base, or in base 10, if you want to write it in that way. Similar here, we have 725 by 8. So this will be 7 times a to the 2 plus 2 times a to the 1 plus 5 times a to the 0. So this is going to be 7 by a squared is 64. And then 2 times 8 is 16. And a to the 0 is 1, so this is just going to be 5. Now, this is going to be 7 by 64 is going to be 448. And so plus 16 plus 5, this is going to give me around 469 now on base 10. Now we have something in hexadecimal. So we have B3A16. And so to represent this, we first got to remember what is each of these things. So remember that B is going to be 11. It's going to be represented 11. And this is going to be times 16 power to the 3. Then we have 3 times 16 power to the 2. To the 2 here, to the 1 here. We only have 3 digits. And then A is going to be 10, and it's going to be times 16 power to the 0. Okay, so this is going to be 2,816 plus 48 plus 10, which at the end is 2,874. Now, last we have 2,417 base 8. So that's going to be 2 times a to the 3 plus 4 times a to the 2 plus 1 a to the 1 plus 7 times a to the 0. So now if we find those numbers, we have that this is going to be 1,024 plus 226 plus 8 plus 7. And so this is going to be at the end 1295 in decimal base. All right, so now for question number 2, we're actually going to be doing the opposite. We're going to convert something in decimal number and go to binary or octal or hexadecimal or base 16, depending of the number, and we're going to be using repeated division. Okay, so first we have 231, and we're going to pad that to binary. So we're going to always divide by 2. So 231 divided by 2, that's going to be 115, and it's going to have a remainder of 1. And we cared a lot about the remainder because the remainder is the representation of our new number. So now we have 115. And we're going to divide that by 2 again. And so that's going to be 57. And our remainder is just going to be 1. And remember, we get this by doing 2 times 57 plus 1 should give me 115. Okay? This is just like the remainder theorem. Now, 57, we're going to divide that by 2. So 57 divided by 2 is 28. And once again, the remainder is going to be 1. 2 times 28 is 56 plus 1, 57. Now we take 28 divided by 2. This is going to be 14. And the remainder is going to be 0. And then I can go 14 divided by 2. And that's going to be 7. And our remainder is going to be 0. And then I have 7 divided by 2. And that's going to be, of course, 3. And our remainder is going to be 1. And then I have 3 divided by 2. And this is going to be 1. And the remainder is going to be 1. And then, of course, 1 divided by 2 is 0, with remainder 1. So now the way that we're going to set up our number is we're going to go backwards. Notice that we have here we have this 1, 1, 1, then 0, transition 1, 1, 1. So we're going to represent this as 1, 1, 1, 0, 0, 1, 1, 1, and binary, so base 2. So now this is my new representation for 231 and base 10. Now let's do the same thing for 469 to octal base. So we do the same thing. We take 469, we divide by 8, and we're going to find the number that is. That is 58. And the remainder here is going to be 5. Now we have 58 divided by 8, and then that's going to be 7, and the remainder is going to be 2. And now finally we take 7 divided by 8, but 8 is not in 7, so this is going to be 0 times, and the remainder is just going to be 7. So now this is going to be in base 7, and in base 8, sorry, is going to be 725 and base 8. Okay, so we'll start from the last remainder to the first remainder, and this is our representation. Now C, we have 2,874 to hexadecimal. So we're dividing by 16 in here. So if we divide by 16 this number, we're going to get 179, and we're going to get that the remainder is 10, or that will be A. Okay. If we take 179 and we divide it by 16, then we're going to get that that fits 11 times, and we're going to have a remainder of 3. Now last, and 11, we're going to have that 16 doesn't fit. Okay, so 0, and our remainder is just going to be 11, or B. So we can kind of represent on base 16 this as B3A on base 16. Now last, to finish this type of examples here of question number 2, we have 1,485 to base 9. So we do the same thing, 1,485 divided 9. And that's going to be 100. Let me actually compute this. Yeah, so if I have, this is 165, and the remainder is 0. And now if I pick 165 and divide by 9, this is going to be 18. And the remainder is going to be 3. Now if I divide 18 by 9, then that's going to be 2, and the remainder is 0. And so last, the 2 divided by 9, 9 doesn't fit in 2, so 0, and the remainder is just going to be 2. So now our new representation is going to be 2030 on base 9. Okay? So now for question number 3, we have something similar. We want to convert each of the following decimal numbers into binary, octal, and hexadecimal. All right, so 231 base 10 in binary is something that we already discussed. We did it here on this first one. So we can represent this as this. But now we're transforming the same number to octal in hexadecimal. So let's actually do that. So the easiest way that you can do this by doing groupings, but you can also do it by simply just dividing. So 231 divided by 8 is going to be 28, right? And 28 times 8 is 224. So the remainder to get to 231 will be 7. Then I'll take 28 divided by 8. And that's going to be 3. And so the remainder will be 4. 3 by 8 is 24. To get to 28, you'll have 4 more. Then you have 3 divided 8. And that's going to be 0 times. And of course, then that's going to be 3 on the remainder. So on base 8 is going to be 347 on base 8. Now I'll do exactly the same thing for hexadecimal. So 231 divided by 16, that's going to give me 14. And the remainder is also going to be 7. Then 14 divided by 16 is going to be 0. And then the remainder is, of course, going to be 14. Which, in terms of letters, of course, that's going to be representing E. So this will be E7 on base 16. Okay? So now, same thing we do for 4,532. So first, we can do this by divided by 2. And so we can start doing division by 2 on this, and we get all the remainders possible. That's going to be a very long calculation, so I'm just going to give you the end result. So when I start doing all this, then the representation is going to be the number 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 2. Remember, the idea is the one as always. You start by, okay, so this is 4,532. So this is going to be 2,266, and then the remainder is 0. And then here you go with 2,266 divided by 2. You go to the next, and so you get 0 here, 0 here from this remainder, and you start going and going until you get to this point. Okay, so now to go on base 8, which is a little bit more quicker, we'll start just divided by 8. And then we do the same thing. We get the remainders here. So when I go with base 10, with base 8, I'm going to get that this is 10,664 on base 8. So doing the same process of the remainder that we've been doing. And finally, on hexadecimals, we're dividing by 16 and getting the remainders all the time. And when you do that, then you're going to get that this is 1B4 on base 16. Okay? So, so this is just cutting some of the process that we will do, but we're exactly doing the same that in question number 2. So hopefully this, make sure that you practice this and you get to the same results, so you have a clarity on how to achieve that. Now, another thing that we can do for transformation is we can use bit grouping shortcut. So instead of doing repeated division, we group together. And so if we group together and we have certain information on how some of those groupings are going to have or are going to be represented, then you can pretty much simplify everything. So for example, the 1010 in base 2 can be transformed to hexadecimal as A. So this pretty much, if you have 10, 10, 10, 10, which is what we have here in base 2, this is like having AA, or this is going to be AA base 16. Notice that I'm grouping blocks of 4 digits here to do a representation of what this is. Now, if I'm doing this in octal, then I gotta do it on group of 3. And so, for example, and I gotta go from the right. So, for example, to represent this into octal, I'll be doing 0, 1, 0, and this will be representing 2, 1, 0, 1, and then this will be representing 5, and then 0, 1, 0, and this will be representing 2 again. So this will be 252 on base 8. Notice that the way that we do this is we have 0, 1, 0, 1, 0, 1, and then 0, 1, and we have a 0 in front that we don't have here, so we have this one here. Okay, so same thing is if we're going to transform this 80E base 16s to binary, we're going to replace each of the hexadecimal digits with its number. So for example, 8, the representation on binary is going to be 1, 0, 0 on 2. And 0 is just going to be 0, 0, 0, 0 on base 2. And E is going to be 1, 1, 1, 0 on base 2. By the way, you might be thinking, why is this representation? Notice that the order of the power. This is 1 and 2 to the 3. What is 1 and 2 to the 3? Is just 8. Similar thing with E here. This is 2 to the 3 plus 2 to the 2 plus 2 to the 1. And 2 to the 3 is 8. 2 to the 2 is 4. 2 to the 1 is just 2. So it's 8 plus 4 plus 2. So that's going to be 14, which is E. So we're just arranging the representation of numbers on binary by blocks of 4. So that will be that will mean that the representation dex in binary will just be 1, 0, 0, 0, then 0, 0, 0, 0, 0, and then 1, 1, 1, 0 on base 2. So we reorder pretty much in the same order to write that number into binary. Now this 572 on base 8 to binary, we can just rewrite it on terms of what is this each of this number representing on base 2. So 5 is just going to be 1, 0, 1 on base 2. 7 is just 1, 1, 1 on base 2. And 2 is just going to be 0, 1, 0 on base 2. Notice this is 2 to the 1. This is 2 to the 2 plus 2 to the 1 plus 2 to the 0. So 7. 2 to the 2 plus 2 to the 0. So 4 plus 1, 5. We have the we have the representation of the digit in the new base. And so now in this way, we can write 1, 0, 1. And then 1, 1, 1, and then 0, 1, 0 on base 2. So this is a shortcut for avoiding some of the repeated division, but you gotta know some of the basic numbers that you wanna use.